Welcome to another exciting video lesson brought to you by Vision Concept Academy. In this lesson, we'll be looking at heat energy, and we'll start quickly by defining the term temperature. Temperature is the degree of hotness or coldness of a body. So this is the foundational definition of temperature, is the degree of hotness or coldness of a body. So temperature in itself is a scalar quantity. It's a scalar quantity. It is a property of an object which decides which way the heat will flow. For instance, we know that temperature is measured in degrees Celsius or degree Kelvin. And we know that if a body is hot, this value will be high. For degrees Celsius, the highest is 100 degrees centigrade, or 0 degrees centigrade, that's the lowest. So if the body is hot, energy will flow from the hotter parts of the body to the colder part. That is what we mean by that. The body, the heat is a property of an object which decides which way heat will flow when it is placed in contact with another object. So heat flows from the body that has higher temperature to the body that has a lower temperature. So when heat is applied on the body, when the temperature increases, what is the effect of heat? Effect of heat. So on a body, number one effect is that it will change the temperature. So we're talking about the reading, you understand, the reading of the body, that is in terms of measurement of temperature. So it will change the temperature of the body in the sense that the temperature will increase in value. So the temperature will actually increase. Number two effect is that it will change the state of the body. It will change the state of the body, change the state of the body. So what is the state, or what is the state of the object? You have different states. Number one, you have the solid state, you have the liquid state, and the gaseous state. What this thing means is that a body can exist in these kinds of forms. You understand? It's the same constituent, but it is existing in this kind of form. So if, for instance, heat is applied on the body when it is in solid form, it will go to the state liquid. It will melt. Or if you continue applying the heat on the liquid, it will now become gaseous. The molecules of the body will now gain more energy, and to now break the force that is keeping it together. So the second effect of heat on the body is the change of state. The third effect of heat on the body is expansion of the body. So you agree with me that some metals will increase in length when heat is applied to them. So it will increase in length, or some objects will actually increase in size when heat is applied to them. So number four effect is it will change the physical properties of the body. So heat will change the physical properties of the body. So it will change physical properties. Some example of such properties can be electrical properties, or resistance, or the magnetic properties, or the conductivity of that material, the density, the color. These are physical properties of the body that can change because heat has been applied. All right, so the fifth effect of heat on the body is thermionic emission. Thermionic emission. We will see this later in this course. Thermionic emission. Thermionic emission is when heat is applied on some metals, then the electrons begin to evaporate or begin to escape from the surface of that metal. that is emission. Okay, then I will stop at this. Is not exhaustible, but I'll stop at this. Change in pressure. Change in pressure. So when you apply heat to an object, you see that for if it's a gaseous state object, the pressure of the gas increase, and so its volume will also increase. So these are the effects of heat on a body. So we move on to the next discourse. We'll be looking at the kinetic molecular energy. Kinetic molecular energy. I'll just describe what it is. Kinetic molecular energy. So here we tend to use this model to explain what happens to the body, that's the molecules that makes up a body. So the kinetic molecular theory assumes that number one, that every substance is made up of tiny particles called molecules. So every substance is made up of tiny particles called molecules. Every substance. So if I have a substance like this, there are tiny things, tiny molecules inside, and they are held together by some special kind of forces. And these forces make them to acquire the shape, especially if it is a solid state matter. So this molecule are together, they have regular patterns that is binding them. You see regular patterns. They are held together by strong intermolecular force. And this is responsible for the shape of that particular matter. So that is the first assumption. Second is that the molecules are at constant state of random motion. So the molecules are at constant state of random motion. These molecules inside here, the molecules are at random states of constant motion. So that's another postulate of the kinetic molecular theory. Okay, I meant to say theory here, not energy. It's a theory. Okay, so this is the second assumption or second postulate, that the molecules are at random motion at a state of random state of constant motion. So even for the one that is solid, the molecules are vibrating at the particular point. Why? Because the force, this between here and here, all this, I'm trying to expand it. All this between two molecules, you understand, there's a force holding them. So if they cannot leave that position because of that force, they can be moving about that position. They can be, if it can remain on this point and be twisting and turning. It's movement. So the molecules are at random state of constant motion for solid. Once the heat is applied on this and the molecules now begin to go apart far from how they were before, you see that there is to and fro movement, within a confined space. So at the liquid state, there's more space in between the molecules or particles. There's more space, and there are some restrained movements in between the molecules at the liquid state. Okay, so we say that there is constant motion, and we say that they are colliding elastically with one another and changing their direction as a result. So they are colliding with themselves and changing direction as a result. Now, number 3 here says that there is always an attractive force between the molecules. So there's always an attractive force between the molecules. So, like I said, Even for the solid, the attractive force is greater because the space in between the two molecules is small. For the liquid, the attractive force is not as strong as this, but it still exists. It still exists. And for the gaseous state, you see that. Okay, let me just label this as solid, as liquid. So this is solid liquid. Then there will be a state for gaseous where the molecules are far apart, far apart. So for gaseous states, you see that the attractive force is smaller here. Why? Because the distance between two molecules is wide. Distance is very wide. They are far apart. So the attraction is not as strong as this. And conversely, this one is not as strong as this. This is the strongest in terms of the force of attraction. And finally, for kinetic molecular theory, the volume of gas molecules is negligible. The volume of gas molecules is negligible. So the volume of gas molecules is negligible, very small, cannot be considered. See, cannot be considered. So kinetic theory explanation for temperature. So how do we explain use kinetic theory to explain temperature? I've alluded to the fact that temperature will cause this one to move faster. Okay, let me just let me explain it for us. Let me just explain it for us. Let's do this. Okay, so kinetic theory explanation of temperature. So how do we explain temperature? Kinetic theory explanation of temperature. Okay, so like I said, temperature is the degree of hotness or coldness of a body. The degree of hotness or coldness. So we're explaining kinetic theory, kinetic molecular theory. So if I have a solid state like this, a solid object, this solid, I said the particles that makes up this are very neatly packed together. I'm trying to represent it as much as I can. Packed together, so that the distance between the two, a two molecule or between two molecules is very short, very small. Now this is liquid. For the liquid, I have the molecules, the distance is further apart, than this one. And for the gaseous or for gas states, you have something like this. So you see, everything is represented, relatively by the distance between two molecules. You understand? Okay, so now, since the molecules of a substance are in constant motion, for this one, the motion is about the point. It is turning, twisting, turning. You see, it's not changing, it's not moving as per se, because if it moves, the shape of the solid will be distorted. So that's why the solid maintains a particular shape. It maintains a particular shape. It does not change. We are looking at it, it does not change. You understand? So, but the particles are moving about a point. For this one, there is little room for movement to and fro. That is why the liquid, if you pour it on a container, it will assume the shape of the container. It will flow from a higher level to a lower level. So there's movement of these particles, but still restricted. But for gas, the restriction is removed. Gas can just go, the energy from one of the particles can make it move away from the other particles. So gas can move. Gas can only be contained in a container. But this one, the particles are moving, faster. So I want to explain this with the kinetic theory. I want to explain temperature. Temperature changes from solid to liquid if heat is applied. So this change to solid to liquid and change to gas if the heat is continuous. So that's so change and this change. So it changes. Why? Because you apply heat continuously and this moves from here to here. So since the molecules of the substance are in constant motion, they possess kinetic energy. So this one has kinetic energy, but it's very negligible. Very, very negligible. Very negligible. If zero, because it doesn't move from its point. doesn't even move from its point. It is here you now start can quantify, the movement. Okay, so temperature of the body is a measure of the average kinetic energy. So as heat is applied here, temperature increases. Now this temperature that's increasing is actually causing these molecules to start moving. So the temperature of the body is the measure of the average kinetic energy. That is the definition of temperature. That's one definition of temperature. Addition of heat to a substance cause the increase in the speed of motion. So as the heat is applied here now, the speed, the molecules begin to have greater speed. Understand? Okay, so the molecules, and hence an increase in average kinetic energy of the molecules. So the kinetic energy increase. Average means that, okay, by the time I calculate the speed of all the molecules together, averagely the kinetic energy has increased. Okay, so you see that if the average kinetic energy increase, temperature will also increase. So it goes from heat affecting the speed of molecules. The speed of molecules affects the kinetic energy, and the kinetic energy increases the temperature. Temperature will increase. So once heat is applied, the speed of the molecule increases, kinetic energy will also increase, because kinetic energy is like this now. This is how kinetic energy is. So this is speed. If this one is increasing, this one is increasing, and kinetic energy also increase. So temperature will increase. So temperature is related to heat, and it comes from the fact that because the kinetic energy has increased, temperature will also increase. Okay, so now we'll go to one of the effects of applying heat on the body. We mentioned many effects of heat on the body, many effects, and one of them is the change of the expansion. So I'm going to discuss thermal expansion, thermal expansion, okay, or expansivity. Let me make it more scientific. Thermal expansivity, CVT. Okay, so what is thermal expansivity? Okay, I will explain by saying when heat is applied to solid, liquid, they expand. They also contract when this body cools down. So expansion means increase in size of an object. So we looked at the kinetic molecular theory before, and we said that heat can cause the molecules to start having greater speed. Understand? Look at how we said. I said when you apply heat, the molecules you have molecular speed will increase. Molecular speed increases. Then when the heat continues, kinetic energy increases. And when kinetic energy increases, kinetic energy is actually the movement. You understand? The movement, the energy that. So from this energy now, we now see that temperature will increase. Okay, so expansivity. If temperature increases, okay, if molecular speed increases, it means that the body, if for instance for solid now, the body will want to, assume more space. You see, because the tightness is not enough. So it wants to assume more space. So it will, at this point now, the space in between them will increase because the molecules are trying to get new grounds. That is why expansion occurs. Okay, so that's kinetic molecular theory explaining why expansion will occur. And then there is a body can expand linearly, areally, or cubically. Linear expansion. Linear expansion is when the length of the body increases. Linear expansion is when the length of the body increases. Okay? So linear expansion is when the length of the body increases. So there is a term known as linear expansivity. Linear expansivity is defined as the change in length per unit length per degree rise in temperature. So this one now is the length, initial length, L1. When heat is applied, it now increase and now acquire a final length, L2. But mind you, there was an initial temperature here when it was L1. So when it now become L2, there's a final temperature. So therefore, linear expansivity is denoted by this symbol. Is defined as the increase in length, L2 minus L1, that is initial length from final length, over per initial length and per degree rise in temperature. This is the mathematical formula for linear expansivity. You see, look at it here. Initial length is L. From here to here, initial length. When heat is applied, or when temperature increases, heat leads to increased temperature. So I'll be using this term heat. Understand? When heat is applied, the temperature increases, and when temperature increases, the molecular speed of all these particles increase, and they want to find new ground. But for solid, if it's still in solid state, they can still slightly maintain the original shape of this. So as it increases like this, there's a final length that occurs. Understand? So from this initial length and final length, these are two parameters already. And there's an initial temperature where this was before, and when the heat increases, it rises up to a final temperature. So these parameters is what we use in deriving this. So this expansivity, linear expansivity, is the change in length per unit length per degree rise in temperature. This line here, quotient line here, is a pair. So the definition here is linear expansivity is the change in length from L1 to L2. So that's the difference. Per unit length per L1 per degree rise in temperature. So from this formula here, let me define them. Okay, I'll do it again. L2 minus L1 over L1 into theta 2 minus theta 1, where this is linear expansivity. It's a constant. Linear expansivity. It's a constant. And L2 is the final length at final temperature. Final length at final temperature. L1 is initial length at initial temperature. And theta 2 is final temperature. Then theta 1 is initial temperature. So these parameters is what define linear expansivity. So it is actually measured in this theta. Linear expansivity is measured in degree C, per degree C, or per degree Kelvin. Per degree C or per degree Kelvin. Okay. So we're going to quickly do an example. So at this point in time, if you're not subscribed to our channel, kindly subscribe to our channel to get more lessons in physics, math, and chemistry. All right, so This example here says a copper rod whose length at 30 degrees C is 10 meters is heated to 50 degrees C. Find its its new length. See the word they are using? New length. Then take linear expansivity for copper. For copper, I told you that linear expansivity is a constant as 0.000017 per Kelvin. See how they write the units per Kelvin. Okay, so this is actually the question. From this question, we can deduce the parameters. So the parameters, you say a copper rod whose length at this. So this is the initial temperature. So what's the length at the initial temperature? L1 is equals to 10. Theta 1 is equals to 30. Find a new length. We're looking for L2, and L2 is not given. Then theta 2 is what? 50. Expansivity is given as 0.000017 per Kelvin. Okay, so just this is the formula: L2 minus L1 over L1 theta 2 minus theta 1. So we're looking for what? L2. So this is what we're looking for. Make it series of formula. So L2 is equals to L1 plus theta L1, expansivity L1 theta 2 minus theta 1. So this is it. So you plug in the parameters. L1 is 10 from here, plus expansivity is 0.000017. L1 again is 10, open bracket and close open bracket, 50 minus 30. That's the change in temperature. So L2, by the time you compute this one mathematically, you get your L2 as 10.00344 meters. Okay, meters, because the initial one is in meters. So at this point, if you're not subscribed, kindly subscribe to our channel so I can get more exciting videos as we upload them. Okay, so move ahead. We'll go to the next one: area and volume expansivity. So I will advise you to look for more examples, more worked examples, identify the parameters, and solve. So area expansivity is the increase in area per unit area per unit degree rise in temperature. So it's like this. So it is the increase in area per unit area per degree rise in temperature. So this is area or superficial expansivity. So if you see this word, superficial expansivity, if you see this word in your exams, please note that it is the same thing for area. The next one is volume expansivity or cubical expansivity. So this one is denoted with this symbol, gamma. It is the increase in volume per unit volume per degree rise in temperature. It's easy to define all these things with formula. In fact, in your exams, if you just write this as the definition and break it down and say where this is this, this is this, this is this, you have defined it. Formulas are used to define, concepts in physics. So this is the area expansivity or superficial expansivity is equals to A2 is the final area and A1 is the initial area. So A2 is final area at the final temperature. A1 is the final area at the initial temperature. So anything you are given, you can get it. Now there's a relationship between the cubical, the superficial, and the linear expansivity. So I'll just put it here. Relationship between linear, superficial, and cubical expansivity. Cubic, that's the word. Cubic expansivity. Okay, so how are they related? So this one is equals to 2 this, and this one is equals to 3 this. So what does this mean? It means that the area expansivity is equals to 2 times the linear expansivity, and in the same vein, cubic expansivity is the same thing as 3 times the linear expansivity. So you can be given a question to resolve. Sometimes you'll be given the parameters to get the linear expansivity, and okay, so you get when you get it, you now say, okay, what is the cubical? What's the area? You just multiply it by 2, and what is the volume? You just multiply the linear by 3. So we'll stop here for today. I hope this video has been informative for you, and I'd like to thank you for viewing.